Hi, welcome to lecture 9. This is part 1 and we are going to talk about principal components. Okay? So the agenda for today will be an introduction, then I'm going to talk about estimation of principal components, and finally how we choose the number of components. Okay? There are many references. For a textbook treatment, I recommend Joliffe, principal component analysis, and there are a bunch of papers giving results with respect to the theory of principal components. Okay? So let's start with the motivation. We have a data set that we call X, which contains capital T observations, observations over time of n variables, n indexes like the size of the cross-section. Okay, so we also assume that each variable was previously the mean, so we save the data on this vector, this matrix X that will be that will have like T rows and n columns. Okay? And suppose we want to extract as much information of X as possible and construct another data set called Y with the same T observations, but with only K columns, and this number K is much less than N. Okay, so we are kind of reducing dimensionality, right? And we define Y be Y1 up to YK. Okay? In other words, we want to compress the data set without losing too much information. Okay? So if we have a high dimensional data with many correlated variables, principal component analysis will allow us to reduce the dimensionality of your data, okay, such that most of the variation that exists in the data across many high dimensions will be captured by fewer dimensions. Okay, so that's the mechanism. So PCA is a very versatile tool. It can be applied in many different situations, such as visualizations of large data sets, efficient use of resources like compression and noise reduction, improving data quality, pre-treatment of the data for further machine learning algorithms, so we can reduce the dimension of our data set, have less variables than in the beginning, and then feed machine learning methods such as the ones that we studied in the course with these new components, with that this new data set will have a dimension that will be smaller than the original data set. Okay? So in fact, it can be applied to any situation where we want to reduce the number of features that have some dimension reduction. Okay? And it's very simple to be computed. It's just a kind of a rotation of the original data set, but it's a rotation in a very smart way. Okay? So suppose let's take a two-dimensional case. We have a bivariate correlated Gaussian, so it's highly correlated. As you can see here, we have kind of the a line here. So there's a kind of a regression line here, if you want, like showing the correlation between these two variables, right? And the idea is that one like to rotate in two different dimensions, because if we look at this, imagine that we take this data set and we project the data set on these axes. So the data will range in all these among all these values. Okay, and if we do the projection on the y-axis, okay, we also have a large variability, right? So the idea is that can we find a rotation, but such that the first axis explain most of the variance? Okay, so how we are going to do that? To be very simple, we take one direction. So if we project our data on this direction here, the first direction, we are going to have large variation. And the second direction there, if we project here, so we have project the data on this axis, okay, on this direction, we are going to have this variability. If we project on the first direction, we'll have all that variability. Okay, so it's the first direction accomplishes most of the variation in the data, and the second direction takes just like the residual variation. Okay? So it's a very powerful technique. So how we find this new set of axes? How do we determine this rotation? Okay, so we denote sigma. It will be the sample covariance matrix of x. So let's call sigma 1 over t x prime x. Okay. Sigma is symmetric, but might rank less than n, if for instance t less than n. So everything that I'm going to tell you now is under the assumption that t is larger than n. Okay, so we have more time observations than cross sections. If it's the other way around, you just basically do everything on the transpose, and everything will go through. So the idea is to find a vector which lives in the n-dimensional space of real numbers, okay, such that the sample variance of x times gamma, okay, is maximized. So that's going to be the idea. Okay? So the sample variance of x gamma will be given by 1 over t gamma prime x prime x gamma, and this will be equal to gamma prime sigma gamma. Okay? So without any additional constraints, we can pick a very large gamma and obtain an infinite variance. So this is not really useful. So we need kind of more restrictions to make the technique sound. Okay. So what we are going to do is that we are going to restrict the norm of this vector gamma that we are trying to find. So we are going to restrict the norm of gamma to be 1, or equivalent gamma prime gamma should be 1. So we call these unitary vectors. Okay? And we want to solve the following constraint optimization problem. So we want to maximize the variance of x gamma subject to the restriction that gamma must be a unitary vector. Okay, so the norm, the L2 norm of gamma should be 1, the square of L2 norm. So gamma prime gamma should be equal to 1. So the Lagrangian is given by gamma prime sigma gamma minus the Lagrange multiplier lambda times the restriction. Okay, gamma prime gamma minus 1. So we want to solve this optimization problem. Okay, so we have to find first order conditions for the Lagrangian. So what we are going to do, we take the derivative of the Lagrangian with respect to gamma 1, okay, and make it equal to 0. So once we do that, we get this equation. Okay, and this is kind of an eigenvector equation, but this is a matrix. Okay, this is kind of the eigenvector, this is the eigenvalue, and the eigenvector again. That's how we solve eigenvalue, eigenvector problems. Okay? So lambda 1 is the eigenvalue associated with the eigenvector gamma 1. Okay? So which pair of eigenvector and eigenvalue should we choose? Okay? So let's see how we are going to pick this pair of eigen. So these are kind of, so the first thing you have to notice that the first order condition of the optimization problem tell us that the solution, okay, is a pair eigenvector eigenvalue, okay, and that vector that we are looking for is one of the eigenvectors of the matrix sigma. Okay, so we want to find which one of them. So if we recognize that the quantity to maximize it is, look, so we want to maximize the variance of what's going to be maximized. We want to maximize the variance of x gamma, right? Which is gamma prime sigma gamma. So it's what we have here. But from the first order condition, from the eigenvector equation, we know that sigma gamma 1 is equal to lambda gamma 1. So this is equal to gamma 1, lambda 1, gamma 1. But this is a number, so this is equal to lambda 1, gamma 1 transpose gamma 1. Okay? But by our restriction, this is equal to 1. So, bingo, what we saw is that the quantity that we want to maximize is one of the eigenvalues. So this is an eigenvalue of 1 over t x prime x of sigma. So, but we want to maximize this, so which eigenvalue we pick? The largest one. So we should choose lambda 1 to be as large as possible. So the solutions pick the eigenvector associated with the largest eigenvalue of sigma, and then we have the first principal component. As easy as that. So let's call y1, that will be x gamma 1, the first principal component of x. Okay? And its variance will be given by lambda 1. Okay, so that's the first rotation of the data. Okay. Now we have the first one, we have to compute the second one. So the second one, it also wants to maximize the variance. But we want that second component, that vector, to be orthogonal to the first one. It should be sample uncorrelated, the second principal component to be sample uncorrelated to the first principal component. So the sample covariance between x gamma and x gamma 1, okay, it's given by 1 over t, x gamma prime, x gamma 1. So this is equal to lambda 1 gamma transpose gamma 1. And this comes from the fact that we have the eigenvector equation here. Okay? So the restriction imposing PC1 and PC2 to be uncorrelated translates into requiring that gamma and gamma 1 to be orthogonal. So basically gamma prime, gamma 1 should be equal to 0. Okay? Therefore, how we're going to find the second principal component? We want to maximize gamma prime sigma gamma, subject that gamma is a unitary vector, but as well that gamma and gamma 1, the previous one, they are orthogonal. Okay? So gamma prime, gamma 1 equals to 0. Then we have the Lagrangian. We have a new Lagrangian multiplier, phi, because we have two restrictions. We take the first order condition. We left multiply the above equation by gamma 1, and we get this equation here. So basically, we need that phi to be equal to 0, and what we obtain from the first order condition is this expression here. Okay? again another eigenvector equation. So again, the solution is eigenvector eigenvalue equation. Okay, so we are going to same strategy for choosing gamma 2. So it will be the eigenvector associated with the second largest eigenvalue. Okay, and we have the second principal component will be y2 equals to x gamma 2. Okay? And the sample variance of the second principal component will be lambda 2. Okay? And then we keep continue like this for all the others. Okay? We basically maximize the variance, we get an eigenvalue eigenvector equation, we pick the JF largest eigenvector, the JF largest eigenvalue, and the associated eigenvector. Okay? And the PCs will be given by yj, x gamma j, and gamma j is selected by the method that I have just presented to you. Okay? And so given the desired number of principal components, something that will be between 1 and n, we can collect all the vectors gamma in this matrix, gamma k, okay? And we can construct the vector, the matrix of principal components, the new data set that will be t times k, not t times n anymore because we reduced the dimension. We call this yk, it will be equal x gamma k. And by construction, the columns of this new data matrix Y will be orthogonal random variables and with sample variances given by the eigenvalues. Okay? And the sample covariance matrix of Y will be a diagonal matrix with the lambdas on the main diagonal. Right? So, now the question is, how can we choose k? And here we have a trade-off. If we set k equal to n, we do not lose any information, but there is no reduction in dimension. Okay, so you're just making the data set orthogonal. If we set k equal to 1, we reduce a lot, but we miss too much information depending on the data structure. So we have to trade off these two limit situations, okay? And we hope that there is strong redundancy in the data such that we can drop some of the components without losing too much. Okay? So we have like few variables. We explain most of the covariance structure of the original data set. Okay? So one idea is to start running a full PCA k equals to n and plotting this quantity alpha j. That's the relative contribution to the total variance from each component. Okay? So this is the ratio of the lambda j, that's the variance of the jf component, divided by the sum of lambdas, that's the total variance. Okay? And so that's exactly what I said. So usually we can find data sets around 50 variables that the first 3 principal components, let's say, can explain more than 90% of the variation. This is not uncommon for us to find in practice. Okay? So this is an example of some data where we plot alpha j, and you see that the first principal component explains almost 80% of the variation, and the rest are kind of just minor contributions. So in this case, with a single principal component, you are going to explain most of the variation without losing much. Okay? So, but how? Let's go back to the question: how we select number of PCs? So there we can have a rule of thumb. For instance, stop at a k such that the following principal component do not add much to the already explained variance, say something less than 3% of marginal contribution. Okay? Or choose the number of components such that a large portion, like predetermined, say 90% of the variance is explained. Okay? We can do that. Okay? Or we can look at the biggest drop, so that this paper by Onatsi, where he suggested looking for the biggest drop, computing the ratios of the eigenvalues. So you select R, will be the number of components as the argument that maximizes the ratios of two adjacent eigenvalues. So we look at the largest relative contribution to the total variance with respect to the previous component. Okay? Or something that's kind of getting more popular nowadays is that get all of them and run a lasso and let lasso, adaptive lasso, elastic net select which principal components are more important if you have a target, right? Because if you just want to reduce dimension and like to compress data, you don't have a target. We are basically doing unsupervised learning. Okay? So basically what I presented to you is just unsupervised learning. But suppose that you have a target variable that you want to use these principal components to explain the behavior. So like the paper that I presented last week, where we have like 500 variables, we want to take principal components and of these 500 variables and use them to forecast future inflation. So we can basically run a lasso of future inflation on the principal components of the data and see how many of these components the lasso will choose. Okay? So this is one possibility. To summarize, let's see what's the PCA recipe. So take a data that's uncentered, x tilde, center the data. So the first thing to do is to center the data, and so you're going to have the x. Perform eigenvalue, eigenvector decomposition of the sample covariance, 1 over Tx prime x. Organize the eigenvalues in descending order, and sort the eigenvectors according to the eigenvalues. Okay? Choose the number of PCs, pick the first k eigenvectors to construct the matrix gamma k, and construct the new data set yk. So this very simple 6 steps. Okay? So you don't really need to run the maximization problem. But I just showed the maximization problem to prove to you that this is equivalent to run an eigenvalue eigenvector decomposition of a matrix. Okay? So any software like Python or MATLAB can do eigenvalue eigenvector decomposition of a matrix. How is PCA used in finance and economics? First, macro forecasting, the example inflation forecasting, transform large number of macro variables into a small set of macro predictive factors, use these factors to forecast macro variables. Term structure modeling, so you have a large number of yields and you model the dynamics of these yields into a small number of curve movements, and this can be used like in hedging. Okay? And you can also summarize a large set of variables and feed these principal components into dynamic models or VAR models, vector autoregressive models, to forecast, for instance, volatility, macro variables, asset prices, so on and so forth. Okay? Stochastic discount factor, we can model the SDF. If you took a course on asset pricing, SDF is a key quantity. You can write the SDF as a function of a small number of factors, and these factors can come from principal components. Okay, so this simplifies a lot the determination of the SDF, and you can even use lasso on top of the principal components. Okay, and of course there's a modeling decision of how many factors, how many variables. So it's kind of density of the model versus sparsity. Okay? So let's take an example, nothing related to economics, but in image compression. So just let you see how these things work in a very practical and interesting application. Suppose that you have this butterfly and you want to compress it, okay? So how we transform this image in data? So the original butterfly picture is composed by 372 times 492 pixels. Okay, that's the definition of that image. Okay? Each pixel is in the grayscale from 0 to 255. So this is a matrix of numbers ranging from 0 to 255. Okay? So let's make each observation 12 by 12 grid, so that each observation is a 144 dimensional vector. So we have n equals to 144. Then the number of observations that we stack everything, we divide the pixels and we stack, is t is like 1271. Okay, so 1271. And so let's apply PCA, trying to reduce this 144. So this is the original image. So we are taking, so that's already compressed image. So we have like 144, but we are using 6 principal components. So comparing to that picture, we almost see no difference. It looks the same picture. Okay? Now if we reduce to 16 principal components, we start to lose some definition. 6, we lose quite a lot, but we still recognize that's a butterfly. So if you just want to recognize which animal is on the picture, you can easily detect that's a butterfly. That's with 3. Still not bad. Of course, with 1, it's very difficult to distinguish what's on the picture. But that's kind of very high compression, right? But if we take 144 dimensions and we move to 60, so it's more than 50%, you almost lose anything. Maybe you are losing details that we cannot even eyeball. Okay? Even with 16, I think it's pretty good. Okay? And so we can look at the numeric eigenvectors converted back to the 12 by 12 pixels to see which group each principal component is kind of selecting. Okay, so this is for k equals to 60. So this shows what we are kind of combining, which kind of elements we have. Okay? And this is for 16, and this is for to 6, the 6 principal components. How we weight everyone, each of the 12 group of pixels. And this is for k equal to 3. And if you look at the error that we have, the recovery error, if you want to see the original, compare with the original picture, we see that we have the error is kind of high if you have like just one principal component, but if we are around 50, it's already very, very small error. And of course it converges to 0 if we go back to 144, but there's a huge compression. So that you can use if you use like 25 principal components, you have already dropped the error dramatically. And as I showed you, can still see the butterfly on the picture. Okay? So this is our first block. I hope you have enjoyed it, and I see you on the second block.